Welcome to the pre-recording of this lecture 41 of MCS 260 Introduction to Computer Science. So this is the 21st session at the start of the last week in the 8-week summer course. So we are nearing the end, and what I want to introduce today are some more advanced programming techniques and problem solving techniques. So in the early days when computer programming was introduced, you could see problem solving with Pascal, for example. Um, Recursion is a very powerful programming technique and a problem solving technique as well. But when it works great, but there are things that can going wrong. So that is why it's not really properly embedded within this course, but it comes a little bit towards the end. And in this lecture, in this last week, actually it is almost the last session because we start to review. After that, I will also would like to hint a little bit at other computer science courses. So there is a course in data structures. So I mention here the stack of function calls. We have encountered the stack. We can see a Python list as a stack, but the stack merits more attention in a data structures course. So that is why recursion and stacks are also related. With a stack, any recursive algorithm can be transformed into an iterative one. So in some sense, what we know already should suffice. Uh, However, there are other aspects that need to be addressed to fully work with recursion well. What is the running example that I will be using in the first half of the presentation or of the lecture? I will be using the factorial. So one can introduce um, the recursive programming also as a rule-based programming. So there are two rules to compute the factorial. So for n equals 0 and n equals 1, the factorial is just defined to be 1. So it's for a natural number. So every time we give an algorithm, we say that the input, so the input is an integer that is non-negative. That's a natural number. So the second rule defines the value for n factorial as n times the factorial of n minus 1. So I wrote the rule here: if we know the value for n minus 1 factorial, then there is this property that n factorial is n times that value. So it's written as a sentence. So the exclamation point is the natural notation, how mathematicians write the factorial. So the factorial should not be seen here as similar to a point at the end of the sentence. Um, there is this connection with rule-based programming. There is also the connection with proof by induction. So this is a course, Introduction to Computer Science, that is taught at the sophomore level, second year. So in the second year, you may also take a course, or you know already what mathematical proofs are. So you can first, in a proof by induction, you first verify the trivial and the base case. So we have a statement that we want to prove. We verify that it holds for the simple cases of the inputs. And then we assume that the statement holds for all values smaller than a given size, than a given case. So for all the simpler cases, the statement holds. Then that's the induction hypothesis. Then in the second part of the proof is extended. So there is a transformation that happens. You can reduce the general case to a case that is simpler. And that's actually also what this rule, the second rule, says. You can reduce the computation of n factorial by n times a factorial of a lesser number. So this is a very important problem-solving technique as well. The divide and conquer methodology takes a problem, splits a problem into easier cases, just by assuming that you're not yet in the trivial case. If you're not in the trivial case, you split things up into smaller problems, you solve the smaller problems, and then you are assembling the solutions to the smaller problems to the original problem. Recursion is also a technique that leads to parallelism. So we introduced parallelism before in an earlier lecture. Somehow, how this is still a proper part. One technique to discover parallel algorithms is also by reorganizing a computation. Some computations benefit from a recursive thinking, even though in the actual realization and the actual computation, we actually often proceed them in an iterative fashion. I mentioned the stack of function calls. So here is how the factorial is computed. So when the computer sees factorial 5, then 5 is not a base case. So the call will be made for 4. Then the 4 is still not the base case. Then the second call number 1, will be leading to call number 2, factorial of 3, still not in the base case. We are going for factorial of 2, still not in the base case. We do the factorial of 2. That will lead to the third and next call. So the last call is when you are in the base case and we are returning 1. So there is the stack of function calls, which I here list. So this is the output of a program. So this printing of the trace information is very useful to see how the computer is actually handling this execution mechanism. So the stack we have seen with threads as well. Stacks are used for scratch space. So what the computer needs to put on the stack is the argument. And we push to the stack and then we pop from the stack when we return. So the return value is then realized, replaced on the stack. The return value then replaces essentially the function call. We are multiplying the result of that function call by the current argument. So actually you walk backwards. So a stack, think about a pile of books again. That's what I should have mentioned right away. So you are actually pulling off like a pile of books, one after the other, the function calls that are pushed on the stack. So the computation is done. So everything is computation. So also, but the computation is done first with the data structure. So, and the computations that are done here are the decrementing of the numbers. And then we do the multiplications of the natural numbers. So here I wrote it in symbolic form, but what is returned is the number 120. Okay, there is a stack of function calls. So, and here you see the recursive factorial. So Python is very good in working with very long numbers. So we are, in this example here, the factorial of 79, we are long exceeding the hardware integers, but as a Python programmer, we can continue doing this, except that at some point there will be an error. I will demonstrate this in the Jupyter notebook. There will actually be a first error that is uh, related to the integer string conversion. So there is a limit there, but there is also the maximum recursion that. So it used to be 1000, and that's why 1000 with 2034 will fail. But now the current recursion that, at least in my installation of Python, is at 3000. So at this time, we have covered many topics about Python, and we have seen our fair share of errors. You can actually write an exception handler and then to compute it iteratively. All right, here is again the stack of function calls. This is the connection with data structures. So data structures is an entire course that follows, is one of the follow-up courses needed to gain a better understanding uh, on algorithms proper. So programs consists of algorithms and data structures. Here is the growth of the stack again. So when you get to the base case, you actually have an entire stack. There are cases we will not go in there, but there are cases where you have to be careful. The stack can grow exponentially. So the fact that Python has this recursion limit there is to make sure that your data structure actually really doesn't explode on you. So there are cases where you should not use recursion naively. But again, this is outside the scope of this course. What is not outside the scope is how you can reason about programs and how you can add extra print statements just to show what is happening. So there is the tracing info. There are tools, by the way, that also will allow you, so debugging tools that will allow you to do the step-by-step execution of a program. Um, I will introduce the notion of an accumulating parameter. So to make the printing nicely, as on the previous slide, I had spacing. So the level of the depth of the recursive, the depth of the recursion, was actually made visible by the number of spaces. So in the previous slide here, I was at the maximum depth of the recursion, and I was printing that many spaces to indicate. And you could imagine here the pile of books where you have actually the smallest book on top with the smallest argument and the biggest argument at the bottom, biggest book at the bottom. So we are using an accumulating parameter to make that printing. It's important, so the other thing and the most obvious thing, and again something that I should have mentioned this earlier, that it can go wrong just like with any loop. You have to make sure that it terminates. So the termination is here ensured is that every argument is actually decreased. So we get closer and closer into the base case. And we can also predict, so the factorial is a very predictable computation. We actually know well in advance how long the stack will be. The accumulating parameter goes up. So the accumulating parameter is actually explicitly keeping track of the depth of the recursion. We have only one recursive call. Recursion is very powerful to build trees. Trees, another important data structure that you will go into in a data structures course. Here our tree is having only one branch. Here you see the evolution of the two parameters. So we have the number that comes in and then the accumulating parameter k. And we are using this accumulating parameter to do the printing properly. There are other usages of these accumulating parameter. You can accumulate the information that is happening, so we can reverse the order of computation. So here we're doing only the multiplication when we return. Perhaps you may also want to have you may want to do that computation sooner if you want to keep track of the size of the numbers. So um, so we have this limit. I will show how you run into the integer string conversion. You could actually set this dynamically if you can predict how your number is growing. Um, so the code that is here, so normally I wouldn't put code on slides, but you can also see how powerful recursion really is. You can write really short code and get a lot of work done. So here I am using an accumulator no longer to keep track of the depth of the recursion, but I'm actually computing the factorial. The important point which I glossed over also, so it's important that this lecture consists in two parts. I will certainly have forgotten other things, but the initialization is important. Here you can see that we must initialize the factorial to 1 because in the base case we return the value of the factorial. In the general case, we are going to accumulate the value of the factorial. So the multiplications are done at the same time when we are decrementing the parameter. So often, in any case, if you are designing recursive functions, having an accumulating parameter is very useful for you as a programmer to keep track of the depth of the recursion. And you may want to, we've seen computing over the internet. If you want to write your own web crawler, we have seen how to download pages from the internet. In a web page, you can look for where the anchors are to other web pages, and you can go to there automatically. Now, so the search actually quickly expands, and you may want to limit the depth of your recursion. All right, so tracing the factorial computations. So here you see how this is done. So again, I'm trying to enforce the same idea of printing, but now with the extra accumulating parameter again. And just to indicate that the popping actually now can go very quickly because there is no computation that's actually happening. This is a data structure computation. We each time essentially move the stack pointer, or we don't do this. It's the computer that moves the stack pointer for us. The order of the computation is a little bit different. So actually we start by not by the smallest number, but we actually start by computing 1 times 5 and then 5 times 4. So the numbers come out in other order. So in some sense, the numbers are starting to grow faster, if you like. Here is the tracing of the factorial, doing this automatically. with the extra parameter. Now there are two accumulating parameters. There is a parameter that controls, or that monitors, not controls, that monitors the depth of the recursion. So the recursion is typically controlled by the first parameter. So that's a good style guide as well. So a function can have many arguments. A good style guide is to put the most important parameter first. Here, in recursive algorithms, the parameter that controls the depth of the recursion and how close we are to the base case is going to do this. Um, okay, factorials, you can just compute them better iteratively. Um, Palindromes is a problem-solving technique. So it's another way to think about programs and algorithms recursively. So what is a palindrome? Palindrome is the same word if you can read it forwards and backwards. Here are some examples. In a way, list comprehensions are very important in Python, and in some sense this is part of the review as well. If you have to solve this in Python, so for a word, you will apply the reverse method on a list. That's a method that is built in, so Python comes with batteries included. If you have to solve this, you can do this with the instructions here, and just a comparison of two strings will do it. The program that we will write will work both for lists and strings. So strings in Python are uh, seen as an elementary data types that makes Python actually more powerful. But in reality, strings are actually arrays of character types. So that's why they are somehow seen as elementary, because arrays are the basic building blocks of scientific computing. But essentially, we can use the strings also as they are listed with the indexing. So here is the problem that we will solve. We will write a function is palindrome. The instructions on a former slide actually solve this, but we will work with an iterative version. This is to introduce the divide and conquer method. Sorting algorithms are important in a subsequent course because sorting occurs in so many places. How do you sort? Well, you first check if you have one or two elements. So these are the base cases. Then you split the list in half, you sort the halves, and then you merge. So that's the algorithm for merge sort. An algorithm that runs in n log n time. Very important, as we have seen in an earlier lecture. So here are the base cases. So in rule-based programming, you would look at the cases, the trivial cases. If somebody gives you an empty word, then it's indeed also a palindrome. If there's only one character, and then you check two character words. You could also say that's still a base case, but you can reduce this to the empty case. So you check whether the first and last character are different. If they are different, then you return false. So in some sense, this could be a lot more efficient. Most words are actually not palindromes. And you just check the first and the last character, and that's it. So recursion might seem a lot cumbersome, but in search methods, and I mentioned the super linear speed up with searches in an earlier lecture. Well, this could be a case here. So typically this is an algorithm that runs in size, in a time linear proportional to the size of the word, but in most cases, most words are not palindromes. You can solve this in a constant time just by comparing the first and the last character, and that will be handled by a base case. This is sometimes contrary to general advice when you think of algorithms. Don't think about too many cases, but it depends on the application. If your application, um, we talked about exceptional cases when we talked about exception handlers. So if most of your words are not palindromes, then you can write this actually a lot more efficiently than by reversing all the characters in the words and comparing the two words. All right. Um, Fibonacci numbers. So Fibonacci numbers and oops. So there is a middle exercise that should be removed. Um, Writing C is not part of this course. So remove this exercise. Um, I will remove this from the posted side. So it's important, Fibonacci, if you do this naively, and here you have to be careful. This will show that you have an exponential number of function calls. So exercises 1 and 2 are actually important. With memoization technique in a later course, we can actually write efficient recursion by storing the results of function calls. So this is now that I said memoization, you can probably figure it out how to do this yourself. You can keep the original recursive definition of the Fibonacci numbers, but use a dictionary to store the result of the function calls, and that will do it. Um, um, that's it. So that's the first half of the lecture. So let me now go to the Jupyter notebook, where we look into the code. Um, so we have the lecture that restarts again. Most likely I have omitted things about this. So here you see the definition as I wrote it up as a mathematician. So on the slides I was more thinking inwards, but for simplicity, n is a natural number. If the natural number is 0, then the factorial is 1. If the natural number is positive, then you are multiplying n times n minus 1 factorial to get the result. And that is somehow embedded in this code here, except that you can be a little bit more efficient also when n is 1. So here the code that corresponds to this would be the n less than or equal. So LaTeX is not strictly part of this course, but if you are taking uh, a, a mathematical proof course, most likely your instructor will appreciate if you type up your proofs with LaTeX. So here is the corresponding mathematical notation now. If the number is less than or equal to 1, you return 1. Otherwise, you have the recursive function call. Okay, so if you test this, test the factorial for the base cases, and then with the list comprehension, we have the first 10 factorials. The numbers are going rapidly, so this is a case where you can experience overflow. But you can see here, so on the slides I had the exception handler. So this is function with an exception handler, which should actually run all the time, except that we have this other error. So we have the value error that is raised. So I probably should fix this. So if a runtime error or a value error. So and now I can run this for any number. and the kernel has died. Okay, so that is about, let me try it again. So there is something that causes this problem still to be fixed. So let's not do this then. So this was kind of the largest I could go. And now I see what is the problem. So the exception handler will actually trigger itself again because the first exception that I have is the value error. And I was thinking very naively that I could actually uh, handle the value error also with increasing the digits. So, and I did it wrong. So let me fix this now. Okay, this is very good. So we have seen that we can handle multiple exception handlers. So the exception that, to make this more robust, if accept value error, what will I do? I will set, so I have to import sys, so use this to increase the limit. Okay, I have to type it in. Set the int max string digits. Int max string digits. Any value, so there is a reason why it's set to so many digits. Perhaps 100,000 might be too ambitious. Okay, I have my set, and then I happily erase do return factorial. But now, what do we have? I have to try the, I will do the recursion again. So here you see the problem. The problem is that I will do the statement again. So it may still not work because the problem is that now I have a try that I would do except for an exception handler. So this is very bad. So it may indeed lead to a problem. So giving up, return -1. Okay, so this works for the simple case, but let me now see what happens when I type in 9. Okay, so there is still a problem here. So I should not have tried to do this. That's the reason why I'm exceeding. So it may have been that. Oh, I thought that this was a global. There is still a problem. So the exception handler is then also not really done. I should have checked this better. So there is the set recursion limit. So that's another problem. So, but the value error is already occurred, and there is the printing that is done. Okay, I will not look for this. I should actually point out at the fix for the recursion limit. For the recursion limit, the error that the runtime error that worked, and you have to believe me for this. So this was when the recursion limit was still at 1000. Then actually we have the iterative. So I want to point at the iterative algorithm. If you really have to compute a factorial, the efficient way to do this is the iterative way. So there is the normal way how we have done all our loops in this course. This is now we call the iterative way. Okay. Um, Okay, so improvising at the spot is not a good way for writing code. So I run prepared code. Here you see the tracing of the factorial. On a Jupyter notebook, I can be a little bit more ambitious because of the size of my screen is better than the size of my slides. So you see the code and the output. So the value of an accumulating parameter here is that it accumulates and it computes the depth of the recursion. So each time when I do a recursive call, so that is done here in the general case, the value is incremented. Why is this also important? Remember on the midterm exam, I wanted you to complete a table with all the values of the parameters. The k is not a local variable. The k is a formal parameter. So it's just a name that refers during the instance that refers to the variable in the context in which it was called. So when I call, so it could be an extremely complicated exercise to actually draw in great detail all the objects that are involved here. So the k is referring to the 0 when this is called at the first time. When it is called the second time, there is another k, but k takes the value k plus 1. So if we are running this program, we are computing values for the arguments. So k plus 1 evaluates to 1, and then there is a next k, so it's a formal parameter. It's a next k that's going to refer to 1. The first argument NBR is referring initially to 10. Inside this function call, there is, if you like, a local variable that holds the value of 9, NBR minus 1, and the formal parameter inside the call, when this is called again, the NBR there, so there is another NBR, which is a formal name that will refer to the 9. One can make a very nice drawing, but for 10 it might be getting too complicated, except that perhaps not, because it's a linear, uh, it's a tree with only one branch, so it's very straightforward. So you will have here 11 or 10 numbers, 10 numbers from 10 to 1, so there is the countdown as you go closer and closer to the simpler case. But there is also the increment, so the increment of the recursion parameter as you get closer and as you get deeper and deeper into the depth of the recursion. And at the end you have at the base case. And at the end you see 10 factorial. So 9 factorial is this, and 10 factorial multiplying by 10 is just adding a 0 at the end. So I hope that this example shows a little bit two things. The stack of the shows many things. It shows the stack of the recursion. It shows the concept of the recursion depth. And you could see in some sense this is a very complicated computation, iterative method is preferred for here, but it is a good example. The recursion actually grows linearly in size. What actually is growing is and that was the first exception we hit, was actually the exception for the size of the numbers. We can change the order in which we do the computation. So here the next script, also something that I forgot to point out is the k needs to be properly initialized. So it needs to be initialized here to 0 as we are adding up. If you want to change the order of computation, so you may not like that we are uh, doing our multiplication at the very end, but we want to do the multiplication as we go along, then you can change this so you can actually accumulate the factorial. And here I pointed this out. The initialization, as with any loop, is actually critical. Okay, then the last program on this factorial problem has the two accumulating parameters. So there is the accumulating parameter. Now I cannot put everything on one slide, or perhaps I can. So it can fit on one screen. So we have the code, a bit longer. The code prints out the stack properly formatted with the depth of the recursion. The last parameter is now counting how deep we are in the stack, or how high the pile is of books, if you like. And also we have the result that is accumulated in this parameter. um, the code is still done with the percent operator, not with the formatting strings. So that is still something that merits improvement. And that is a blank line at the very end, also not good. Okay, now you see it completely. All right, factorials, you have to compute them iteratively if you really must. But in the recursive problem solving, so here is the divide and conquer strategy. A very useful principle. Check whether you're not in the base case, so split the program in simpler cases, solve the simpler cases, and then assemble the solutions to the simpler cases so that you have the solution to the original problem. Multiple base cases might be needed. So in the case when we want to detect a palindrome or not, this function will in general be very successful, as most of the words are not palindromes, and you can see that already from comparing the first with the last character. So in some sense, if we are concerned with efficiency, then if you would look at all the words, and you can actually compute the probability, not even all the words that you can find in a dictionary, but all possible words. So the chance that actually you need to compare every single character, and this would be the half of the characters, so the palindromes are actually the worst case. That's another case. Another argument for kind of saving half of the time already is an important thing. So we are mostly in this course interested in correctness, but the first solution with the reversing of the lists is way too expensive. So traditional programmers of my generation, of when I grew up, people who were teaching were mainly concerned with efficiency. So saving already half of the time is already important. So this program comes closer to it, and it is still correct. You use a lot more time with a stack of recursive calls. So you will also have as many recursive calls as the half of the length of your words. For long words, again, this could be a problem. Um, Here, race car is kind of the word but perhaps I should first emphasize the solution. So we have multiple base cases, which is a good reinforcement of the elif keyword, the nested else and if. So I have three base cases. First base case checks the length of the word. Then we compare the first and last element of the word. It's a good exercise also for indexing. And then I check whether the length of the word is 2. So in some sense, if at this case, so if both cases did not return, then it meant that I'm not in this case where first and last letter are the same. So they are the same. So if the length of the word is 2, then actually I have a palindrome of 2 characters long. Okay, so then I have the shorter word. I'm reducing. So here I can do this slicing of the list. I can do the slicing of the list because I know that I'm in the else case. The word is longer than 2 characters. So there is there are at least 3 elements now in this word. And I'm using now the word elements to indicate here that the point that I want to make with the last cells in this Jupyter notebook. This function works on strings and it works on lists. Whether they are characters or not, it doesn't really matter. It would also work on lists, on anything for which the comparison operation is defined. And this is then referring back again through the object-oriented nature of Python. If you are calling this function on any object for which comparisons, indexing, and slicing is defined, then this palindrome function will work. Okay, I hope this lecture was not too confusing. You can see that even I can get in trouble when I improvise with the exception handling. This is towards the end of the course. It's good that I use this lecture to reinforce certain topics. Here, the versatility of strings and lists, how you essentially can convert a string into an explicit list of characters and then also apply the list methods and then join them again. So data conversions are very important. Lists are still one of the prime data structures, also in computer science in general. So there is the language Lisp that stands for list processing, and I hope you can also understand why in Python lists are so important. Okay, with this I'm closing off this lecture. I hope this was interesting. Recursion is a very important problem-solving technique.